Good evening, all. I am Pramod Gaur, Research Fellows, Department of Chemical Engineering, IIT Guwahati. I am going to take a live session on a NPTEL course of Mass Transfer Operation 2, Week 6, Assignment 6 on a liquid lipid extraction chapters. I think all of you have gone through the lectures week 6. So based on that, I am going to take 5 questions. So starting from the MCQ ones, which of which of the following factors favor a formation of stables and more effective dispersions? Option are low interfacial tension, large density difference of the phases, low viscosity of the disper phase, and higher impeller RPMs. All of you know at low interfacial tensions, there is a more stable formation and more effective dispersion. Also required less power consumptions at low interfacial tensions. So your answer of is the answer of question 1. Question 2, an ideal counter-current mixer settler cascade contained in a 6 stages remove the 95% of the solute from the bit. One of the mixer has developed a mechanical problems and is bypassed. For same percentage removal of the solute from the bed, the solvent rate should be. Option are increased degrade may be kept unchanged. None of this. Can anybody tell the answer of this question? It is a simple answer. We have to maintain the same percentage removals. So solvent rate should be the increase. Then it can be attain the this percentage. It should be the increase. All of you got. Going to the next questions. The coefficient of distribution of the solute C between two mutually immiscible liquid A and B solvent is K is equal to IC is equal to XC 1.5. The question are draw the equilibrium curve using the right triangular coordinates, and then what is the slope of the tie line if the mass transfer of mass fraction of the solute in the solvent is IC is equal to 0.2. So here is a given the mutually immiscible liquid A and B. It means that H is equal to B means mole fraction of the solvent in the raffinate phase is a 0, and by A. And mole fraction of the carrier in a extract phase is a 0. I see. I see. Sorry. X. Now this is a raffinate arm. This is a extract arm. Extract at raffinate phase XA plus XB is equal to XC is equal to 1, and in extract phase YA plus YB plus YC should be 1. Right. Now here XB is equal to 0. Here Y is equal to 0. Now here is given a YC 0.2. Put this value here and calculate the YB. So locate this point in extract arm term. This is single one. It denoted by the Q. Then YC point 2 and YB point 8. Now here is a given the distribution coefficient. So based on this equation, we can calculate the EXC. YC I already given. So to locate this point here. So here is the XB is equal to 0. Zero point 0.1. Now connect this to the extra term. This is the tie line denoted by PQ. Now we have to calculate the slope of this PQ lines, which tie line. All of you know the slope formula. Y2 minus Y1 equal to minus this. Put the value here. Is to 0.0833. All of you got this one. Moving to the next one. In a liquid dispersion, the volume fraction of the continuous phase, volume fraction given here, volume fraction of the continuous phase is 0.7. The outer mean drop diameter is 500 micrometer. What is the specific interfacial area of the contact in meter square per meter cube? Given 1 by 5 is equal to 0.7. This 5 indicate volume fraction of the dispersed phase. So here given the continuous phase. So 5 is equal to 0.3. Now 3 outer mean drop here, drop diameter given 500 micrometer. Convert into the meter. Now to calculate the specific interface area, use this equation. 65. All of you got this answer. Moving to the question 5. This is based on the multi-stage counter current extraction. The statement is given. It is a plan to the extract diphenyl hexanes DPH from the solution in the leukosense using pure purpurel as a solvent. The feed rate given 2000 kg per hour with mole fraction of the DPH 45%. That has to be the reduced to 4% in the final raffinate. The solvent rate is given 25 kg per hour. Determine the number of theoretical stages required. Extraction is to be carried out at 45 degrees Celsius. The composition, extract and rapidase arms and tie lines data in mass percentage of the component at 45 degrees Celsius are given below. Given AP is equal to 2000 kg per hour. Mole fraction of solute in feed given 0.45. Rapidate and final rapidate CNs. Okay, solute once mole fraction of the solute in a final rapidate 6 am 0.04, solvent rate given 25, 100 kg per hour, and mole fraction of the solute in solvent 0, means pure solvent. X yes. Now, after attaining the equilibrium, the mole fraction of the solute at equilibrium, calculate, use this equation, mole fraction of solute at mixture F HCl plus solvent HCl and F plus F. This is the EM. Put all the value here. Calculate the mole fraction of the solute at mixture. Point. Now equilibrium data are plotted using the right triangular coordinate in these figures. The tie lines are shown by the light dotted lines. These ones. The points A, S, M, and Rn are located. Rn and M are joined, and the line is extended to meet the equilibrium curve at E1. This one E1. The lines F, E1 and Rn, yes, when extended to meet the difference points. All of you know that these ones difference points. It is a fictitious streams obtained by the removing mass of the feed from the first state extract even, or by removing the mass Rn of the last stage raffinate from the solvent S. It represents the difference points. The formula is this is the difference point. This one. So we have to remove the mass F from the E1 and remove the Rn from the solvent. That is the difference point. The stage being an ideal, the tie line through E1 meets the equilibrium curve at the point R1. The raffinate gas leaving the first stage. Also putting the n is equal to 2. In these equations, that E2 lies, this one, E2 lies on the point of intersection of the R1 and difference point and the equilibrium on these ones. Right. E2 lies on these ones. In fact, R1 and E2 is the operating line for the second stage of the cascade. The tie line the tie line through the point E2 meets the equilibrium curve at R2 due to the ideal stage. Proceeding in the same way, we can draw the successive stage till the point Rn is reached. So the number of ideal stage required for the separation is This is the 1, 1, 2, 3, 4. All of you got this one? There is an alternative way to calculate the ideal stage required for the separations, the graphical constructions. A line emanating from the difference point intersect the extract arm of LLE curve at the point E subscript n plus 1 corresponding to solute concentration Yc is equal to Yc n plus 1, and the raffinate arm at a point Rn, this ones, where x is equal to xen. A few such lines draw a broken lines. This one from a broken line are shown in these figures. The locus of the point xcn and ycn is the operating line on the xc-yc plane on these figures, and the set of xc and yc derived from the these figures and used to draw the operating line on this figure. This is the operating line. This one's the equilibrium line. The equilibrium line is drawn using the given tie line data. Based on these ones. The operating line is also drawn by based on this the data given here. Now to calculate the stages between the equilibrium line and operating line. So draw from the first point, draw the line which parallel to the x-axis to intersect the equilibrium line. Then draw the line parallel to the y-axis to meet the operating line. This is the first step. Similarly other also. So here is the stage 1, 2, 3, 4 is 4.5. The total number of ideal stage is 4.5. So in the previous method we calculate means 4. So here 4 points. So the difference probably occurs because of the error in driving in the tie lines. And this is a simple or more convenient compared to previous ones. Thank you all. I covered all the 5 questions. If you have any doubt, please ask me. Anyone? If you don't have any doubt, I'm going to close the today's sessions. Thank you all. We will meet on next Tuesday, same times on a different chapters, membrane separations.